Dear students, this is Dr. Siva Nagaraju from IARE. Today we are going to discuss problems on ASK, FSK and PSK. Already in theory, we discussed what is ASK and what is PSK, what is FSK. Why? Because all these three are digital modulation techniques. So these topics will run in the course of analog and digital communications in 4th sem. Okay, so let us enter into the topic. So the first one is a course outcome. So this topic will cover in a module 4. So module 4 is covered by CO4. So what the CO4 says: analyze digital passband communication schemes ASK, PSK and FSK using modulation and demodulation process. So already we discussed earlierly in this course what is modulation and what is demodulation and what are the types of modulation and what are the types of communication. Why? Because we're having analog and digital. So in analog we covered amplitude, FM, DSB, SSB, like that. We're coming to the digital communication. We're having different types of digital systems, but modulation techniques are basically these three. One is ASK, PSK and FSK. So we are going to cover the problems in these three basic schemes. Why? Because basic, I'm saying these are the binary. After binary, we're having IARE techniques of that. In IARE, again, we're having QPSK and QAM, different types of that. But we're covering only the binary schemes. Okay. So coming to the first problem, a binary ASK system for equally probable messages using 100 microsecond and the channel has a naught 1.338 into 10 power minus 5 watts per hertz. Determine the peak transmitted pulse amplitude to maintain P. What is the P? Probability of error less than equal to 2.055 into 10 power minus 5. So this is the given problem. Okay. So for this problem, we must know the probability of error formula. So here, these problems are related with formulas. Okay. So coming to that problem. So first we go to write the probability error formula. That is 1 by 2 ERFC square root of EB by 2 N naught. So this is the probability of error. Why? Because in this problem, the last line which is given, the probability of error must be less than 2.055 10 power minus 5. So here we are going to write 2.055 into 10 power minus 5. So this is the condition they given. The probability of error must be less than this 2.055 10 power minus 5. Okay. So now in this, the probability of error we have in given formula 1 by 2 ERFC. What is ERFC? Error complementary function into square root of EB, energy per bit, divided by 2 N naught. N naught is the noise spectral density. Okay. So we are going to find it. So ERFC, the left hand side, ERFC square root of EB by 2 N naught, which is equal to, here in the left hand side we are having 1 by 2. We are sending this 1 by 2 to other side. So it is going to 2 into 2.055 into 10 power minus 5. So by using calculate, you can get multiply this 2 into 2.055 and again you go to send this error complementary function to other side, that is error function. So finally we get EB by 2 N naught greater than equal to 2.9. This is we get. So why? Because we must know that our in computer systems of Simon Hacking, they given what is ERFC tables, error complementary function tables. So in that table, they given what is the value directly they given, or in any exam they given that the function value directly. So there is no problem. We are getting without table in the data given problem data they mention. Okay. So again we are sending this square root to the other side, that is EB by 2 N naught greater than equal to 8.46. So again sending this root to other side. Okay. So finally EB is equal to or greater than equal to 8.46 into 2 into N naught. So what is N naught? Noise spectral density. They given already 1.338 into 10 power minus 5. Okay. So this is energy per bit. EB is the energy per bit. Why? Because this is binary. In binary, you can send 1 bit at a time. So what is that energy of that particular bit? So we are sending either 1 or 0 at a time. That is binary. Okay. But EB, energy per bit, is equal to A square T by 2. A square T by 2. So this is another problem which is related with the amplitude. Energy per bit which is related with the amplitude. Okay. So A square T by 2 greater than equal to 8.46 into 2 into 1.338 into 10 power minus 5. But we know the T. What is the T? Is the time. So it is again related with the bit rate. So in the next slide, we go to here. T is equal to 1 by RB. That is equal to 100 microsecond. So what is A square? So A square greater than equal to 2 into 8.46 into 2 into 1.338 into 10 power minus 5 divided by this 100 microsecond. So finally we are getting, simplify all this in the right hand side, and again the left hand side is A square, send this square to another side, again it goes to root. So we are getting 4.53 volts. 4.53 volts. So once again go to back what they given. So here the given the time is 100 microseconds. 100 microseconds, and N naught, noise spectral density, as 1.338 in 10 power minus 5, and the condition is given, the probability of error must be less than or equal to 2.055 into 10 power minus 5. So here we can see the probability of error we are considered as less than or equal to 2.055 into 10 power minus 5, and again you go to substitute the probability of error in terms of energy per bit and noise density. Okay, so substitute all these values, and again we are using the required formula for solving this. So finally what they ask? Amplitude. So the amplitude is nothing but 4.53 volts. Okay, so this is the first problem. Now coming to the second problem. A bandpass data transmission scheme uses a PSK signaling scheme with x2 of t is equal to a cos 2 pi fct, and x1 of t is equal to minus a cos 2 pi fct. Why? Because here you can know the PSK. What is PSK? Phase shift key. So in the phase shift keying, we know that the phase difference between 0 and 1 is 180 degrees. Why? So that's why we can call it as it is antipodal signals. Antipodal signals. Why? The phase difference between 1 and 0 must be 180 degrees. So here you can see x1, x2 also having a 180 degrees. Here the phase difference is there. In x2 of t, we getting a cos, whereas x1 of t, we get minus a cos. In the bit duration is same, 0 to t to tb, and tb is bit duration. Bit duration is 0.2 milliseconds, and fc, carrier frequency, is equal to 5 fb. The carrier amplitude of the receiver input is 1 millivolt, and power spectral density of the additive white Gaussian noise at the input is 10 power minus 11 watts per hertz. So the NOD is given. The NOD is 10 power minus 11 watts per hertz. Assume that an ideal correlation receiver is used. Calculate the probability of error of the receiver. So here in this problem they ask probability of error. So already we done similar problem in ASK also. But in ASK the given probability of error must be less than some values given. But here you go to find the probability of error of the receiver. Okay. So what they is using the scheme is PSK scheme. So PSK digital modulation is using and sending these two signals. So at the receiver, what the probability of error? So probability of error means how much error is occurred at what probability. So the error is occurring at what probability we are going to measure. Okay. So first you go to write the amplitude of the carrier. So amplitude of the carrier is given as 10 power minus 3 volt. And again another given data NR by 2, that is noise spectral density. Additive white Gaussian noise spectral density, that is 10 power minus 11 watts per hertz. So they given. Another one, they given the bit duration. The bit duration is 0.2 milliseconds. 0.2 milliseconds. So 0.2 into 10 power minus 3 seconds. Okay. So this is the given data. By using this given data, we are going to find the probability of error. Okay. So the normalized power of the carrier in 1 ohm load. Why? Because we must consider load. So here they are not given the load value. So we can take it or we can assume 1 ohm. So P is equal to 1 by 2 A square. So bit energy, EB, energy per bit, is equal to P TB. So EB is equal to A square TB by 2. This is energy per bit. So what is A? Amplitude 10 power minus 3 volts. So 1 by 2 put outside, and 10 power minus 3 whole square into TB. The duration is given as 0.2 into 10 power minus 3. Again it is millisecond. So solving this all, you get 1 into 10 power minus 10. Okay. This is EB, energy per bit. So here 10 power minus 3 whole square. Okay. And again 0.2. So here 6 minus 3. Minus 6 minus 3, you get minus 9. And again 2 will go to cancel, 0.1. Again you can send this as minus 1. So 1 into 10 power minus 10. That is energy per bit. So what is the formula for probability of error for PSK? So in the formula, probability of error is equal to 1 by 2 ERFC into square root of EB by N naught. So this is the difference between ASK and PSK. In ASK, the denominator we are having 2 N naught. 1 by 2 ERFC square root of EB by 2 N naught. That is in ASK. But in PSK, here the 2 is missing. So same function. So the remaining all the same. Only the denominator 2 is missing in PSK. So this is a formula for probability of error. So we know that EB value, we know that N naught value, and you go to substitute all these values and you go to find the probability of error. Okay. So probability of error is equal to 1 by 2 ERFC of square root of 1 into 10 power minus 10 divided by 2 into 10 power minus 11. 2 into 10 power minus 11. So that is 1 by 2 ERFC of square root 5. This is the probability of error. So again you go to use error complementary function tables. Error complementary function tables. We can get the value also, or we can leave here also. No problem. Okay. So coming to the third problem, determine the bit error probability for BPSK system having a bit rate of 1 Mbps. The receiver receives the waveforms x1 of t is equal to a cos 2 pi fct and x2 of t is equal to minus a cos 2 pi fct. The received signals are coherently detected using a matched filter. If A is equal to 10 millivolts and a single sided noise power spectral density is N0 is equal to 10 power minus 11 watts per hertz. Assume that the signal power and energy per bit are normalized. Okay. So here also the same formula you can use, but only the data is different. Why? Here also the same BPSK, binary phase shift keying. So what do you determine? Bit error probability, nothing but PE, probability of error of BPSK, go to find. They given the bit rate. Bit rate is RB is equal to 1 megabits per second. So we have a relation with the time and bit rate, that is 1 by RB. So you get to find TB. From RB you get TB, bit duration. Okay. So that is the given data. And another one is the receiver receives the waveforms x1 of t is equal to a cos 2 pi fct and x2 of t is equal to minus a cos 2 pi fct. So the means here also they can showing the phase difference, 180 degrees phase difference for first waveform to the second waveform. Why? Because PSK sending 180 degrees phase difference for 1 and 0. This is only 1 bit at a time we can transmit. Here the amplitude is same. What is the difference here? Phase is different. Okay, so that is the main theme of BPSK. And after, the received signals are coherently detected using a matched filter. So here the detection process depends on two types of receivers. One is a coherent detector, that is nothing but a matched filter, and another is the correlation receiver. Okay, so here in this problem they are using matched filter. If A equal to 10 millivolts and a single sided noise power spectral density is N0 is equal to 10 power minus 11 watts per hertz. So assume that the signal power and energy per bit are normalized. So normalized power you can mention. They mentioned as normalized power. Okay. Okay. So first write the formulas. A is equal to actually a square. A square equal to 2EB by TB. Or you can write in previously EB. Okay. So again go to the left hand side is a square. A square T by 2. EB is equal to a square by 2. So by using that formula, we are rearranging. We are getting the amplitude. Amplitude is equal to square root of 2EB by T. So how much amplitude given? 10 millivolts. So 10 into 10 power minus 3 volts. And this time with duration or time, they given as 1 into 10 power 6. Why? Because they given 1 megawatt bit rate. 1 megabit. So 10 power 6. So it gives 1 microsecond. Now EB is equal to A square T by 2. So that is equal to 10 into 10 power minus 3 whole square. A square means. So T 1 micro 10 power minus 6 divided by 2. So by using calc, we can simplify this expression. Then you are getting this value is 5 into 10 power minus 11 joules. So hence we have root EB by N naught is equal to square root of 5 into 10 power minus 11 divided by 1 into 10 power minus 11. Here another difference also there. Here in previous problem, N naught is taken as N naught by 2. But here it is taken as single sided. So that's why N naught only constant. Okay. So that is another difference comparing with the previous one. So 2.24. 2.24 we got. So the bit error probability will be PE is equal to 1 by 2 ERFC of square root of EB by N naught. EB by N naught. So we can directly substitute 1 by 2 ERFC of 2.24. So this we can complete up to this point, or we can use error complementary function. Then you go to solve this one. Okay. So in the problem they given this ERFC data. We can substitute what is ERFC of 2.24. We can see in the table. Then you get some value. Then substitute the value. Maybe they are not given. No problem. Leave here also. Okay. So for example, they given. I go to write to 1 by 2. ERFC value of 2.24 is 0.00041. This is ERFC of that 2.24. Okay. In the table, you can see this value. 2.24 value is as 0.00041. 0.00041. So simply you can mention as 2.05 into 10 power minus 4. Okay. So this is the answer. 2.05. This is the probability of error. 2.05 10 power minus 4. Okay. Okay. Coming to the another problem, that is binary data. Binary data is transmitted at a rate of 10 power 6 bits per second over a channel having a bandwidth of 3 megahertz. Assume that the noise power spectral density at the receiver is N0 by 2 is equal to 10 power minus 10 watts per hertz. Determine the average carrier amplitude required at the receiver input for coherent PSK DPSK signaling schemes to maintain probability of error less than 10 power minus 4. So when you consider all these problems which is related with the probability of error, okay, so these are the main problems which covered in the ASK, PSK, FSK, okay. So they are linked with the probability of errors. So here in the fourth one, this fourth problem. So the probability of error is equal to 1 by 2 ERFC square root of EB by EN naught. EB by N naught. This is the probability of error for PSK. So they mention as 0. minus 4. The probability of error must be less than 0.4. So ERFC square root of EB by N naught, which is equal to 2 into 10 power minus 4. So again, EB by N naught, you send this ERFC to the right hand side and substitute the value, you get to 2.6. So EB by N naught, which is equal to greater than equal to 6.9. So sending this square root to other side, you're getting the square. So finally, EB, energy per bit, which is equal to or greater than equal to 6.9 into N naught. So what they given nice spectral density, again you go to substitute the N naught value here. So EB greater than equal to 6.9 into 2 into 10 power minus 10. So this is energy per bit. Again, coming to this, EB, which is equal to A square T by 2. A square T by 2. So greater than equal to 13.8 into 10 power minus 10. So this is EB, energy per bit. But what they mention in T? T is 1 megabit per second. So again, 1 by R bit, it is equal to 1 by 10 power minus 6. So finally, A square greater than equal to 2 into 13.8 into 10 power minus 10 divided by T. So here T is 1 by 10 power minus 6. So here you can mention 1 by 10 power minus 6. So again it goes to A is equal to or greater than equal to 5.26 into 10 power minus 2. So this is the amplitude. So again you can rewrite as 52.6 millivolt. 52.6 millivolt. So this is the amplitude. Okay. So again go to the problem. What they ask? Determine the average carrier amplitude. So they ask amplitude, carrier amplitude. So also find amplitude. So what the carrier amplitude is? 52.6 millivolt. So this is the problem solution for the fourth one. Now coming to the fifth problem. So what is the fifth problem? Binary data is transmitted over a microwave link at the rate of 1 Mbps and PSD. Power spectral density at the input of the receiver is 10 to the power of minus 7 watts per hertz. Determine the average carrier power required to maintain an average probability of error less than equal to 10 to the power of minus 4 for coherent FSK what will be the channel bandwidth. So here they ask two parameters. One is the carrier power and another one is the channel bandwidth. So here also they given bitrate and another one is the NOT, noise spectral density, and another one is the probability of error is less than equal to 10 power minus 4. Okay. So here I'm going to write the required formula, that is EB is equal to A square T by 2. So here the amplitude, which amplitude considering carrier amplitude. So this is nothing but AC. Okay. AC square T by 2. Simply you can write A square T by 2. Okay. So here the probability of error is equal to Q of square root of EB by eta. Here we can mention the probability of error in terms of ERFC, error complementary function, or Q tables. So two ways we can mention the probability of error. One is the error complementary function tables we can use for finding the probability of error, or another one is the Q tables. Okay. So here in this problem we consider as a Q table. Previously we considered as ERFC. So I'm going to say two ways the probability of errors. Okay. Yeah. So the probability of error is equal to Q of square root of AC square T by 2 eta. So here we are writing in the place of N naught as eta. Okay. So which is less than equal to 10 power minus 4. But no, don't mention eta as efficiency. Okay. Okay. Now from Q table, why? Because previously error complementary function tables are using, but here Q tables are using. So Q of 3.71, which is less than equal to 10 power minus 4. So this value is equal to in Q table as 3.71. So directly we can take here AC square T by 2 eta greater than or equal to 3.71. Why? Because on the left hand side we're considering same. The right hand side has 10 power minus 4. So where the Q table which is equal to 10 power minus 4, value is 3.71. So we are taking the 3.71 as this is A square T by 2 eta square root of total term. Okay. So here I require the carrier amplitude. I require the amplitude first. So AC is equal to square root of 3.71 into 2 into 10 power minus 7 divided by 10 power minus 6. 10 power minus 6. Okay. Now AC is equal to 2.35 millivolt. So this is the carrier amplitude. This is the carrier amplitude. Okay. And another parameter which is going to ask in this problem, what they ask? Bandwidth. What is the channel bandwidth? Okay. So here first you go to mention minimum average carrier power. It is 2.35 divided by square root RMS value. Then it is 10 power minus 3. So this is the average, minimum average carrier power. It is 2.76 watts. And channel bandwidth, which is nothing but 1 by TB. So 1 by TB is 10 power minus 6 and it goes to 1 megahertz. So this is the channel bandwidth. The given channel bandwidth as 1 megahertz. We will find. Not given. We go to find this channel bandwidth as 1 megahertz. Okay. Coming to the another problem. So here the binary data is transmitted over a bandpass channel at a rate of 300 bps using non-coherent FSK signaling scheme with the tone frequency 1070 and 1270 Hz. Calculate the probability of error PE assuming A square by N naught is 8000. Okay, so the last problem which is related with the PSK, but this problem which is going related with the FSK. Okay, frequency shift keying. So here what they given data rate at a rate of 300 bps. Okay, 300 bits per second, and FSK frequency shift key. Here non-coherent. See, non-coherent which is considered coherent and non-coherent at the receiver only. But the transmitter, which modulation technique is using here? FSK. So frequency shift key. Already in theory we discussed what is SK, what is PSK, and what is FSK. So these are all binary. That means you can send either 0 or 1. 1 bit at a time. So now we are sending 1 and 0 with different frequencies. That is the FSK thing. In FSK, we are sending symbol 1, symbol 0 with different frequencies. So here they given the tone frequency is 1070 and 1270. So symbol 1 may be 1070 and 0 may be 1270 Hz. Okay. So we are sending either 1 or 0, but with different frequencies. So what they ask? Calculate the probability of error. So here we are going to find the probability of error. So the probability of error is 1 by 2 ER FC, or in another way you can mention exponential minus EB by 2 N naught minus EB by 2 N naught. So we know that EB is equal to A square T by 2. A square T by 2. So we can substitute this probability of error 1 by 2 exponential of minus A square T divided by, so 2 in the denominator again 2 N naught is there. So 2 into 2, 4 N naught. 4 N naught. And what is the given bitrate 300 bps. So T equal to 1 by RB, that is 1 by 300. Okay. So that is going to substitute. So in this problem they are given a T value, N naught value. So A square by N naught, they given 8000 directly. So that you can use. Okay. Yes. So the probability of error is equal to 1 by 2 exponential of, so minus A square T by 2. So that is you can mention as 8000 into TV is 1 by 300. So divided by this 4 into 300. This is the probability of error value. So 1 by 2 exponential. So here you can cancel these two zeros and again it goes to 20. So minus 20 by 3. Minus 20 by 3. So you can use calci What is minus 20 by 3? 1 by 2 exponential of minus 6.67. And finally the probability of error is equal to 6.34 into 10 power minus 4. So this is the probability of error for non-coherent FSK. Okay. Coming to the another problem, 7th one. For an FSK system, the following data are observed. Transmitted binary data rate is equal to 2.5 in 10 power 6 bits per second. Power spectral density of noise is 10 to the power of minus 20 watts per hertz. Amplitude of received signal 1 microvolt. Determine the average probability of symbol error assuming coherent detection. Assuming coherent detection. So where previously is non-coherent version and is a coherent version. So already we know that the receivers coherent and non-coherent. Coherent means with phase difference. We're using the same phase information, then we can call it as coherent version. We're not using the phase information for detecting the signal, then it is called as non-coherent version. Okay. Now P is equal to 1 by 2 ERFC of square root of EB by 2 N naught. Whereas previously you can use exponential. Now we are taken as ERFC. So different way you can use this probability of error, but both are same. Okay. So T equal to you can mention as a bit rate, bit duration, that is related with the bit rate. Okay. And another formula EB is equal to A square T by 2. So these are three formulas we can use in any problem, but they change. For ASK, we can take another probability of error value, and whereas PSK, we can take another one. Okay, but these three are same: energy per bit duration, probability of error. You can go through all these problems. You can having same parameters you can consider. Okay. Okay. Now we go to substitute A square. So what is the amplitude? As 1 microvolt. Okay. That is 1 into 10 power minus 6 square into T. So T is bit rate. Here the given transmitted binary data rate is 2.5 in 10 power 6. So that you can use. But it is RB. But we are asking T. So it is 1 by RB. So 1 divided by 2.5 into 10 power 6. That is T value. But 2 is missing. So here 1 into 10 power minus 6 whole square divided by 2 into 1 by 2.5 and 10 power minus 6. So solving all this, you can get 1 by 5 into 10 power minus 18. So what is 1? This is nothing but EB. Okay? This is EB. Now PSD, power spectral density, is equal to N0 by 2. That is equal to 10 power minus 20 watts per hertz. Watts per hertz. So EB by 2 N0 is equal to 1 by 5 into 10 power minus 18 divided by 4 into 10 power minus 20. So again you go to solve this one. Simply get 5. The value is 5. Solving all this we get 5. Okay. So probability of error is equal to 1 by 2 ERFC of square root 5. Why? Because 1 by 2 ERFC of square root of this EB by 2 N0. So EB by 2 N0 value got 5. So go to substitute this root 5. So 1 by 2 ERFC of root 5 value is 2.23. Then you go to IARE table. So you go to check where 2.23 value gives. So probability of error is equal to 1 by 2 into 1.84 into 10 power minus 3. So here 2.23 value gives in the IARE table as 1.84 into 10 power minus 3. Okay. So finally 0.92 into 10 power minus 3. So this is the probability of error of FSK. So IARE table we must have. Okay. Or they given a problem. EFC value. Okay. So don't worry about that one. Now coming to the 8th one. Binary data are transmitted at a rate of 10 power 6 bits per second over a microwave link. Assuming channel noise AWGN with zero mean and power spectral intensity and the receiver input is 10 power minus 10 watts per hertz. Find the average carrier power required to maintain an average probability of error. Probability of error P less than equal to 10 power minus 4 for coherent binary FSK. Determine the minimum channel bandwidth required. So they asked here the bandwidth, and what they ask also, find the carrier power, average carrier power. So to maintain the average probability of error is 10 power minus 4. Okay. So what is one? What's this technique? So this is FSK. So this is binary FSK. So what is the binary FSK probability of error? That is equal to 1 by 2 ERFC of square root of EB bar 2 and not this one. Okay. But the probability of error must be less than or equal to 10 power minus 4. So this total value is going to equal or less than 10 power minus 4. Okay. Okay. So the P probability of error is given as 10 power minus 4 or less than equal to minus 4. So ERFC of square root of EB by 2 N naught is equal to 2 into 10 power minus 4. Just I am going to substitute in the values in the given formula. Okay. So ERFC of U is equal to 1 minus ERFU. So error complementary function in terms of error function. Here ERFC means error complementary function. ERF is error function. Okay, so the difference is 1 minus of error function. So square root of EB by 2 N naught equal to 2.7. So EB by 2 N naught, you can send this square root to another side. So we are going to square. So it is approximately equal to 7.29. But what they given? N naught by 2 as 10 to the power of minus 10 watts per hertz. So EB is equal to 7.29 2 into 2 power minus 10 divided by, so sorry, this is only EB, so not requirement of any region. So go to multiply all this is 7.29 into 4. So it is nothing but 29.2 in 10 power minus 10 joule. So this is energy per bit. Okay. So the data rate here given as 10 power 6 bits per second. So the bit duration is here 10 power minus 6. Why? Because we know that TB is equal to 1 by RB. So by using this formula, you can directly write TB is equal to 10 power minus 6. So now the average transmitted power or average carrier power is nothing but EB by TB. So 29.2 into 10 power minus 10 divided by 10 power minus 6. So finally 29.2 into 10 power minus 4 watts. This is the average power, average carrier power. Okay, so here for maintaining probability of error less than or equal to 10 power minus 4, the average carrier power is 2.9 milliwatt. You can write 29.2 10 power minus watts or what it may be. So the minimum channel bandwidth required is approximately simply 1 by TB. 1 by TB again comes to RB. So nothing but 1 megahertz. This is 1 megahertz is the minimum channel bandwidth required. Okay, minimum channel bandwidth required for this one. Okay, coming to another problem. A binary FSK system transmits data at a rate of 2 Mbps over an AWGN channel, additive wide Gaussian noise channel. So the noise is 0 mid with a power spectral density N0 by 2, which is equal to 10 power minus 20 watts per hertz. The amplitude of received signal in the absence of noise is 1 microvolt. Determine the average probability of error for coherent detection of FSK. Okay, so this is related to the FSK again. Okay, so here we know that the probability of error. We know that the probability of error PA is equal to 1 by 2 ERFC of square root of EB by 2 N naught, and EB equal to A square T by 2. So we can substitute A value, amplitude is 1 microvolt. So 10 power minus 6 whole square by 2 into T. T is the time. So how much bit rate? 2 Mbps. So 1 by 2 10 power 6. Okay. So finally you can send this 10 power 6 to the numerator. So finally EB is equal to 0.25 into 10 power minus 8 joule. Okay, 8 joule. Now N0 by 2 is equal to 10 power minus 20. The given N0 is noise spectral density or power spectral density is 10 power minus 20, and N0 is equal to 2 into 10 power minus 20. If they are not mentioned, you can take it as N0 by 2. If it is mentioned as single sided, then N0 value only. Okay. So substituting the values of EB and N0 in the expression of P. What is P? Probability of error. The probability of error is 1 by 2 ERFC of square root of EB. 0.25 into 10 power minus 18 divided by 2 N0. Already N0 value is 2 into 10 power minus 20. So again 2 into N0. So 4 into 10 power minus 20. Okay. So after solving all this, probability of error is equal to 1 by 2 ERFC of square root of 6.25. So again using the table of error function. So ERFC of square root of 6.25 is equal to ERFC of 2.5. So that is equal to 1 minus error function of 2.5. So again, we will solve this error function 0.0041. This one. Now the probability of error is equal to 1 by 2 into this 0.0041. So finally we get 2.05 into 10 power minus 4. This is the probability of error. Okay, probability of error. Coming to the 10th problem. So a binary data is transmitted using ASK over a AWGN channel at a rate 2.4 Mbps. The carrier amplitude at the receiver is 1 millivolt. The noise power spectral density N0 by 2 is equal to 10 power minus 15 watts per hertz. Find the average probability of error. The detection is, first one is coherent, another is non-coherent. Take ERFC of 5 is 3 into 10 power minus 6. So in this way they mention here ERFC of 5 is 3 into 10 power minus 6. But here the probability of error detection in two ways. One is coherent, another is non-coherent. Okay. So let us start the problem. So first one is the carrier amplitude AC or A 10 power minus 3 volts. The given RB bit rate is 1 by TB is equal to 2.4 into 10 power 6 bits per second. Another is N0 2 into 10 power minus 15 watts per hertz. So bit energy EB is equal to 1 by 2 A square T. So go to substitute 1 by 2 into A square, 10 power minus 3 into whole square is 10 power minus 6 T. That is 1 by 2.4 into 10 power minus 6. Okay. So this is plus 6. Then EB energy per bit is equal to 10 power minus 12 divided by 4.8 joules. Okay. So now first bit is coherent. Why? Because they given in two ways, coherent ASK. So computation of probability of error in first one is coherent ASK form. So that is P is equal to 1 by 2 ERFC of 1 by 2 square root of EB by N0. Okay. So 1 by 2 ERFC of 1 by 2 square root of EB 10 cube divided by this 9.6. So you get 1 by 2 ERFC of 5. So already the given, we take ERFC of 5 as 3 into 10 power minus 6. So the probability of error approximately 1 by 2 into 3 into 10 power minus 6. So the probability of error for coherent version is 1.5 into 10 power minus 6. This is A bit. For B bit, non-coherent version, probability of error 1 by 2 exponential of minus EB by 4 N0. So again, we go to substitute the probability of error 1 by 2 exponential of minus 10 power minus 12 divided by 4.8 into 1 by 4 into 1 by N0. So what is N by N0? What is N0? This one. So By using calci, you are going to calculate all this, and exponential value also you can substitute. Then 2.45 into 10 power minus 12. This is probability of error for non-coherent version. Okay, so you are going to complete this problem. Okay, so references, the content of information is taken from Communication Simon Hacking and yes, Chitori. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.